9.3. It's a bit of a tricky unit. We deal kind of with right triangles, I think, from here on out. I think the trickiest part is to not be lazy and to redraw triangles in this unit. So whenever you have a problem, I would suggest draw out two triangles that you see that are similar. Altitudes to the hypotenuse. That's a phrase that for a lot of people doesn't make sense. Hopefully, as I explain this first problem, you'll see the altitude and why we call it the altitude to the hypotenuse. So here we have a right triangle. Notice there's my right angle, ABC, and CD is an altitude that's drawn to the hypotenuse of ABC. So here is the hypotenuse, and there is the altitude that's drawn to it. When you do that, three triangles are formed, and we see them sketched out below there. And that's kind of what I would suggest you draw out. You don't need to draw all three of them all the time. I think two of them would suffice. But they give you similar triangles, and so you need to redraw them and to know which parts correspond with which parts. The other thing that I would suggest is using these letters, maybe small, medium, and large, or actually I would call the large the hypotenuse. Label each of the sides. For example, in the right triangle, here we have the hypotenuse, here we have the small, here we have the medium. Here we have the hypotenuse, here we have the small, here we have the medium. Here we have the medium, the hypotenuse, and the small. And I already did the large one. So it's kind of important because you're going to be setting up proportions involving those sides. All right, our first theorem here. We don't necessarily quote this theorem, so we don't need to give it a name. We just use it a lot. And if you want to call it something, I suppose you could call it the altitude to the hypotenuse theorem. But look at the CD to AD. Notice when we talk about altitude CD and AD, we are kind of creating that triangle. And so now let's relate it to this triangle here. So notice I'm referring to the small and the medium, so I go to the other one, and we would say CD is the medium, so DB over CD. Notice how CD shows up kitty corner to each other. That tells us that the altitude, aka CD, is the geometric mean. All right? Let's try this again. I'm going to delete those two and look at AC and AD. Again, we're dealing with the hypotenuse and the small. So I come over here and hypotenuse and the small. So CB over, sorry, yeah, BC over AD, over, get lost, CD. Now there's one other possibility. Notice we don't get the nice little elegant CD showing up in both like we did in the first one. I could go back to the original triangle and notice here we have the hypotenuse and the small, and if I look up above, I see the small and the hypotenuse, and we have AC and AB. So I'm going to erase those. And instead I'm going to use the large triangle and go with AB and AC. Notice when we do it this way, we get that clever little AC showing up in both spots. Therefore, the long leg is the geometric mean. And by the long leg and the altitude here, we mean of the original triangle. Yes? So if we look back at the original triangle and I say, oh yeah, okay, so there's the hypotenuse, that was a geometric mean. This is a geometric mean. And finally, we can see that the medium side is also a geometric mean. Because if we take BC as to DB, so in this case, we've got BC and DB, and if I come up to my triangles up here, I can see that we have the medium and the hypotenuse there. Yes? And so we start off with the hypotenuse, so AB is to BC. Again, note BC. In this case, I guess I got these words turned around, don't I? This is AC is the short leg. And the long leg, in this case, is the geometric mean. All right, we're going to use that rule again and again in this section. Here we go. They give us, in this case, the altitude and then the two bases. So we know that short leg, long leg, short leg, long leg. So 3 is to x as x is to 9. This means x squared is 27. This means x is square root of 27. Again, we can ignore the negative and just rely on the positive, because we cannot have a negative distance. Hopefully that's not a mystery how I got 3 radical 3. Again, you're breaking this into perfect squares, right, and pulling out the largest possible. Again, here we've got the short leg. And so the short leg is the geometric mean between those two pieces. Again, it may be helpful. So we have hypotenuse, short leg, right? And then here we have the hypotenuse and the short leg of the big triangle. So 10 is to x. Doesn't really matter how you write that one initially. And then 10 is to x plus 21. Now this raises a wrinkle because we're going to get a quadratic equation. And hopefully your factoring skills are up to snuff. So we throw the 100 on that side. And now factor time. So again, we've got two factors that when I multiply them, I get negative 100. And when I subtract them, when I add them up, when I subtract them, I'm going to get 21. All right, well, immediately I thought of 20 times 5, but that if I subtract those, I get 15. And obviously 10 times 10 is not going to work. And then I see, oh yeah, 25 times 4, that's going to work. So we'll put a positive 25 and a negative 4. So my two answers are negative 25 or x equals 4. Obviously, we are not going to take the negative 25. Now be careful. Don't discount it every time, because sometimes this negative 25 will work. But in this case here, as you can see that if you can't put a negative 25 there, only 4 would work. All right. A little proof, and then we're done. And by little, it isn't going to be too bad here. I'm going to erase my markings here and just show you what you should probably do as you go through and do this problem anytime you do a proof. Mark? So we know those two are perpendicular. We know those two are perpendicular. And we also know that we have that is perpendicular as well. All right. So we've got altitudes inside of altitudes. I would suggest in this case a little redraw will be helpful. And this one over here. Now, notice PO times PM, right? And then these, PR and PJ, are on this side. So, in between these two shapes is the critical piece. That's kind of the unifying. That's what's shared between them. So I think this is going to be kind of like a transitive or a substitution. If I can show those products are equal to pk squared, then I'll be in business. And sure enough, we can see, or hopefully you can see, let me change color here. Now the hypotenuse is here, this is the altitude, and so this is the long leg, and that is a geometric mean between this piece and this piece, which is perfectly what I'm looking for. And this is the geometric mean, because this is an altitude, between this piece and this piece. So I think we've got this set up. We just got to go through and flesh out the details. All right, first off, we know that pk squared is equal to PR or RP times PJ. And along with that, we're going to use pk squared is equal to PO times PM. And why do we do this? Because the altitude to the hypotenuse theorem. All right. Now by substitution, we can take this piece and set it equal to this piece, correct? So RP is equal, RP times PJ equals PO times PM. I'm going to put MP. And again, this is by substitution. So a nice little short proof. Tricky to kind of figure out how to do it, but once you see the connection of this pk squared, it works out quite nice.